So we now have a description of how, in the context of gravity as geometry, we can describe a universe in which space at any time is isotropic and homogeneous. It's a space of constant curvature, and all that changes is a scale. And we have a natural set of coordinates to describe this. These are coordinates in which are what we call co-moving. You pick where something will be at a given time, say the present, if it is freely moving, and take a collection of freely falling observers that start out at rest at some point and use their positions today, if they're freely falling throughout the history of the universe, to denote the name of a point, and then that observer is, as far as I'm concerned, always at the same position. So these are observers that are at rest, and then relative to them you can have peculiar velocities. It is in these coordinates that the space looks nice and isotropic and homogeneous. It would be nice if we had such observers. We do. By and large, galaxies, we claim, are such observers. They are at rest. Their average motion is the Hubble motion. So galaxies are precisely such an object. And now, having described the kinematics, we now turn to the dynamics. In other words, we have to understand the solutions to Einstein's equations. And we've studied sort of the left-hand side, the geometry. Now we need to study what matter looks like. You would not expect an isotropic homogeneous universe to contain, for example, stars, because certainly if you have a star, then the place where the star is not the same as the place where the star isn't. So matter in an isotropic homogeneous universe has to be itself isotropic and homogeneous. Now one way to do that is to have nothing at all in the universe. That does not describe our universe. And so what we mean is, imagine averaging out over large distances, ignoring little fluctuations like galaxies and clusters. On average, we should be able to describe at large distances the distribution of matter in the universe as completely uniform. So that means there is a constant density of energy, because mass is energy, so we're talking relativistically. There's a constant energy density, rho, or mass if you want, density that is the same everywhere. Otherwise, the universe wouldn't be homogeneous. And if there is a gas with a constant density, then we know enough about thermodynamics to assume that there will be a constant pressure. And these are constants everywhere in space, but of course, they can depend on time. So all of the crazy right-hand side of Einstein's equations about energy and momentum is contained in two functions of only time. There's no variation with position. The equations are going to simplify. Furthermore, we have density and we have pressure. Density and pressure are related by the properties of whatever the stuff is that you fill your space with. For example, if you have an ideal gas, then we know that pressure and density are related to temperature. In particular, we will deal with two extreme cases of equations of state, relations between pressure and density. We have one case which in cosmology lingo is called dust, and so we will be cosmologists and call it dust. What is dust has nothing to do with the kind of dust that causes extinction. The particles, if you will, of this dust are galaxy clusters. Dust is what describes a collection, a uniform distribution of slow, massive particles moving freely and interacting only through gravitationally with each other, or more importantly, with the whole collection of uniform distribution. Because they're moving very slowly, we're going to imagine that this is a zero temperature object. The pressure is essentially zero. So this is the canonical example of dust, of course, is galaxies, slowly moving objects. A collection of dust is isotropic in a frame that moves with it. In other words, in a frame in which you measure the velocity zero. This is not something fancy. Every pilot knows that your airspeed is constant whether you're going upwind or downwind. In other words, the moving air is isotropic in a frame that's moving with the air. It's only when you measure ground speed that you realize that you might not be making any headway trying to go upwind. Your airspeed of your craft is the same. The airplane flies the same way upwind as downwind. It's only relative to the ground that things change. So in a frame where the velocity of the fluid is zero at any given time, at any given place, so at any event, this dust has a preferred rest frame. That's the rest frame in which the dust at that event appears to be at rest. And of course, since we're going to make this dust out of galaxies that are co-moving in the Robertson-Walker coordinates, then what we're going to say is that the preferred Robertson-Walker frame at any point is the rest frame of the dust. That way, they will both be isotropic. Both space and matter will be isotropic in the same frame. And then the other extreme case is very relativistic particles. In other words, the extreme case is particles moving at the speed of light, and we'll call such particles radiation. This can include photons, it can include gravitons, it can include essentially neutrinos, which, even if they're not exactly massless, are very light and move under most circumstances at very nearly the speed of light, or highly relativistic speeds. And you can make a calculation for an ideal gas of relativistic particles. Some of you have followed through in the context of electron degeneracy learning this. And it turns out that for a relativistic gas, since the speed with which the particles are moving is the speed of light, density determines the pressure, and even dimensional analysis will tell you that pressure is the density times the square of the speed of light, and it turns out the coefficient is 1/3, so the pressure of a relativistic gas is related to its density by the square of the speed of light over 3. There's no temperature dependence because a relativistic gas, by definition, everything is moving at the speed of light. And again, you cannot go to the rest frame of a relativistic gas in which the speed of the particles is 0, because they're always moving at the speed of light in all given directions. But there will be a frame, in a specific frame, in which the radiation field looks isotropic. This is the frame in which, if you look to the right and look to the left, you see exactly the same spectrum. And of course, if you're in that frame and someone is at the same place you are in the same radiation field, but they are moving, they will observe a blue Doppler shift in one direction, a red Doppler shift in the other direction, and they'll say, aha, the spectrum is not isotropic. Only one observer at any event sees an isotropic spectrum. That is the instantaneous rest frame. So we have a description of matter, and we're going to assert that the matter is at rest in the Friedmann coordinates, so that space and matter are isotropic and homogeneous in one system of coordinates. And with that in mind, we write down our friend, the Einstein's equations, this time written correctly. There was a latex error that ruined things. So we write here the Einstein's equations correctly, and we insert what we know. On the right-hand side, we insert that the geometry, remember these r's represent curvature, and the geometry is the geometry of a space of constant curvature with curvature r0, which scales with when the distances increase, like 1 over a squared. And then this coefficient k is simply given by 0 or plus or minus 1. 0 means we're in the flat space case. 1 means we're in the positive curvature case. Minus 1, negative curvature case. And in all cases, I can give the same parametrization. In the curved cases, r0 represents the curvature at t equals 0, at the presence, at t equals to 0 when a is 1. At present, in the case that k equals 0, you can put whatever you want for r0 because it's multiplying 0. That's the simplification on the left-hand side. Whereas on the right-hand side, we insert what we know about matter. And what we know about matter, again, is that it's the same everywhere, and it's determined by this one function rho, and then the pressure is, which appears inside the energy momentum tensor, is some given function of rho, depending on what you put in. Okay, so you take all this data, you plug it into Einstein's equations, you do the mathematics. This is one of the cases in this class where I say you do the calculation, and the equations that you find are two equations for one. What are the variables here? The variables are the time dependence of the scale constant. There's no space dependence of anything. So we're trying to determine the time dependence of the scale factor, the time dependence of the energy density, and that's it. We have two functions, and we're trying to find the time dependence of these two. And so we indeed find two equations. They are physics equations. They are differential equations. So watch out. I said we would skate near calculus. So there's this little dot here. This dot means the rate of change of A with respect to time. And we already said if A were a position, this would be its velocity. And we already noted that the rate of change of A divided by A, the rate of relative change of A, is what we'll call the Hubble constant, only we no longer expect it to be constant. So in general, this will be a function of time. And this is given by, Einstein's equation tells us that this is given by the right-hand side, 8 pi g, the c squareds end up canceling, times rho of t. It's the same everywhere in space, but it varies with time. And then this is actually not a part of the right-hand side, obviously. This is a curvature piece. It's another piece of the left-hand side, and we've put it on the right-hand side to get an equation for the Hubble constant. And so the curvature of space and the density of energy both together determine the rate at which the scale factor changes. That's one equation. We need another equation. And so, again, this tells us that the curvature of space, if you want, another way to think about it is if you take the density and the velocity of everything, so that gives you the Hubble constant, that will determine the curvature of space. Space curves in response to the density of energy and momentum, and so the density of energy rho and the rate at which everything is moving, which is determined by a dot, put both of those in, and you can determine the curvature of space. But of course, like all equations, if you know one thing, you can determine another. Everything ends up determined. What's the second equation? Second equation looks even scarier. I have here an A with two dots. If A were a position, this would be the velocity. This would be the acceleration. It's the rate of change of A. And it's related to the Hubble constant by this expression, where this is the rate of change of the Hubble constant, and this is its square. And this is given in terms of the matter distribution by a combination of the energy density, and the pressure. Notice that for a relativistic gas, both of these are in fact equal, because for a relativistic gas, P is equal to rho c squared over 3, whereas for the case of dust, of slow-moving matter, P was actually 0, so this is just rho. And now, this is really a lot of calculus, so let's try to understand what it is that we're trying to say. So imagine that I have some time t star, and I expand A of t and express it for times near t star, and the first term in the expansion was the Hubble expansion term that we talked about before. The next term in the order will be a quadratic term proportional to t minus t star squared, and of course in general there you can expand and get higher order terms. And I will, for dimensional reasons, factor out the factor of h and h squared, and then the coefficient is called q over 2. And notice I put a minus sign here because I understand that gravity will decelerate things, and indeed if I write the expression in this way, so A of t for t near t star is A of t star times 1, which is the value when t is equal to t star, plus a first order term whose coefficient I call h, and then the second order term whose coefficient I call minus h squared q over 2. Q is called the deceleration parameter for good reason, because what it indicates is that if you take, since you're subtracting a positive quantity, it means that if you start as a function of t and you plot A, it starts at t0 at the value a0. The line determined by the Hubble expression would be this constant increase, and what the deceleration parameter does is it slows it down. It decreases below the straight line, and in terms of this deceleration parameter, you can rewrite this crazy a double dot thing as just minus h squared q. It's just twice this coefficient, and notice that the sign here is well justified, because pressure being positive, density being positive, this sign being negative, gravity, ta-da, decelerates expansion. This is not a surprise, but this non-surprising result is derivable with great work by following through Einstein's equation. So Einstein's equations, not surprisingly, tell us that both density and pressure, which is, remember, the pressure results from the velocity or the momentum that the particles are carrying. This momentum contributes to gravitational attraction because momentum gravitates just in the same way that energy does. So notice that the pressure of the relativistic gas actually increases the deceleration, contributes to deceleration, as opposed to one would think, oh, pressure makes things try to expand. Well, pressure makes things expand if you put something in a container, but in this case we're talking about a universe where the pressure is the same everywhere. There's no pressure gradient between inside and outside for the pressure to push on. There's no container for the universe, no edge of the universe for the pressure to push on. Every bit of the universe experiences the same pressure on both sides. What is going on is that pressure contributes to the gravitational attraction because, remember, momentum as well as energy is a source for gravity. Couldn't be otherwise, consistent with relativity. So these are our equations, and they are going to, in the end, determine the evolution both of the density and of the scale constant. However, in general, we will have differing sources of density. Remember, we can have a universe that contains both dust, slow-moving things, and, say, photons, relativistic things. And one can imagine a universe in which these don't interact, and then that means that the energy in dust is conserved, because no dust is created. The total mass, remember, the energy of the dust is just its mass, it's at rest. And so the total mass of the dust is conserved, and separately the total energy in photons is conserved. And if this is the situation when they do not interact, then I know the time evolution of rho of t, if I know the time evolution of a of t. And this is because if you take a given volume, it has some dust in it, and then as this volume expands, it has the same amount of dust in it, but if the distances have grown by a factor of 2, the volume of this region has grown by a factor of 3. So when distance by a factor of 8, and so the density, mass conservation says density decreases like the third power of the scale factor. When space doubles in length, all lengths double, the density decreases by a factor of 8. How does this affect relativistic particles? Well, for relativistic particles, think again about photons, but of course the theory is universal. In the case of a relativistic particle moving at the speed of light, the same property obtains if I take a volume containing a certain number of them. Their number is conserved. When that volume increases, it carries the same number of particles in 8 times the volume. However, they're all redshifted, so the energy carried by each of them is also decreased by a factor of a, and so the behavior of the density of non-relativistic, the energy density of non-relativistic matter is that as a function of time, if there is no interaction and no creation of matter or loss of matter, like, say, the loss of stars, if you wish, convert mass, dust energy into radiation energy, but stars are a small perturbation in the large scale of things. Most of the matter of the universe is interclustered gas, which is not participating in stellar processes. And even when dust is in a star, only a few % of the mass of a star over 10 billion years will be converted to energy. But so this is a small violation of this conservation of energy. Ignoring little effects like stars, then the energy density of dust scales with the scale factor like the negative third power, whereas the energy density of radiation scales like a negative fourth power. Remember, 3 of those are because of this volume, and then 1 extra factor because each photon's energy is decreased by the redshift. Dense slide. Now, Einstein had understood all of these equations. It's the usual case that what you get out of an equation is what you put into it. You put in a lot of symmetry, the equation simplifies. This complicated set of coupled partial differential equations becomes this relatively simple set of ordinary differential equations for functions of one variable time. And Einstein was trying to write the solution that describes our universe. And what he knew about our universe was that it's static. So what he wanted was a universe in which the scale factor didn't change, in which nothing essentially changed. He had no reason to imagine that distances in the universe were changing. He did not know at the time of Hubble's result, which, by the way, had previously been, it turns out, measured by Lemaitre and understood in a deep way. And so he tried to set this to 0, and it's possible to set the rate of change of a to 0 by balancing the energy density against curvature. So you need to have a curved space if you have any matter in it, but if you have positive curvature and positive energy density, you can balance them to get 0 velocity. Glorious. However, you cannot make the acceleration 0, so the 0 velocity, because, of course, both of these terms are all negative, and so the acceleration is always negative, so the 0 velocity solution you found out is sort of like the 0 velocity of my little rubber ball at the top of its flight. It stops for a minute, but its acceleration is still negative. It won't stay at 0 velocity, it'll fall. So indeed, if you have 0 a dot, then the negative acceleration means that you have a universe that is not expanding, but is about to start contracting. So Einstein was very saddened by his inability to find a description of what he thought to be the universe, namely a static universe. But Einstein was nothing if not creative. He looked at his equation and he realized that without ruining any of the axioms or the logic that led him to the equations of general relativity, he could make a modification that would have absolutely no impact on the agreement with Newtonian physics, but would fix this, would allow a static universe. And the correction in terms of Einstein's equation involved adding one more term to the left-hand side. So modifying the way that gravity, the metric function g, is determined by the distribution of energy momentum tensor. He called this the cosmological term. We today call it the cosmological constant. The properties of lambda is that for this to be a consistent modification of Einstein's equation, lambda is just a number, a constant. It has the dimensions, if you work through, of inverse length squared. So lambda is measured in 1 over meter squared. And this is the modified version of Einstein's equations. Of course, you can alternatively think of taking this same blue thing, flipping its sign, and putting it on the right-hand side of the equation, and thinking of good old Einstein's equation in the presence of a different kind of energy momentum distribution. So what kind of crazy energy momentum distribution is lambda? Well, it's a constant, so it does not depend on space, so it satisfies our isotropic and homogeneous relation, so I should be able to describe it by a constant energy density. Indeed, lambda corresponds to a constant energy related to the value of lambda by this. This is what follows from placing lambda in the position where rho sits here. And then the cosmological constant corresponds to a pressure, which is negative rho times c squared. So if you have a positive, and the cosmological constant can have either sign. If it's positive, then it has a positive, corresponds to a positive energy density and a negative pressure, whereas a negative cosmological constant, the roles are reversed. And then, if you now redo the calculation that led us to Friedmann's equations, in the presence of this cosmological term, Einstein finds that the first equation for h squared is modified, and the second equation for minus qh squared, remember here we're determining q, the acceleration, the deceleration parameter, is also modified, but is essentially by exactly the same term. This has to do with the fact that pressure and density are essentially the same thing. And so you plug this thing into that, and what do you discover? What you find is that now I can find a solution where the left-hand side, the rate of change of the scale factor and its acceleration are both zero. How do I do this? Well, I'm going to pick a universe in which p is equal to 0, so my matter is going to be dust. I'm going to, of course, need positive curvature so that the energy density is balanced against curvature. And then it's balanced by curvature, and I'm going to also have a cosmological constant, which will allow the negative term here, this is going to be 0, to be balanced by this term. And it turns out that if you set R0 equal to lambda, remember both of these have dimensions of 1 over length squared, so that even makes sense, equal to this concoction, proportional to the energy density, both of these equations vanish. This is called the static Einstein universe, and Einstein thought, well, since this is the homogeneous, isotropic, static universe, this must describe our universe. He then was informed about Hubble's measurements and realized that our universe perhaps is not static. And this cosmological term was unnecessary. Einstein then regretted introducing this uglification of what was a beautifully elegant equation before. He called it his greatest blunder. As we shall see, it might not have been a blunder. Einstein, even when he blundered, had foresight.